Here's an interesting question about pi, where I'm using pi because it has many, many digits. How many digits of pi do you know? I actually don't know that many of them myself. I only know 3.1415926, and that's it. But pi, as you know, has digits that go forever, and they're very, very strange. And I'm using them to write down numbers in a grid with 113 rows and 355 columns. Here in English, it's written as 113 by 355. And if you're ever doing an exam in English, and it's about a grid or a matrix or an array, the first number counts how many rows there are, and the second one counts how many columns there are. That's why you actually may see that in the Chinese translation, the order of the numbers is flipped because of a different custom. Okay, but the numbers are written one in each square, starting from the top left and then going across and then down. Across and then down means that the first row goes 3, 1, 4, 1, 5, 9, 2, and so on until you get to the 355th digit. And then the 356th digit goes in the second row first column. And then it goes across the second row, and then down to the third row, and so on. Now Alice is going to look at each of the 113 rows. In each row, she's going to add up the 355 numbers and get a number. Now Alice will have 113 different sums, one for each row. And Alice is going to find the average of these 113 numbers. Bob is going to do the same thing but for columns. So Bob has 355 columns, and each sum Bob will calculate, and then Bob will find the average of all of those. Now the question is, what is the ratio of Alice's average to Bob's average? This is a lot of work for Alice and for Bob. It's also a very dangerous amount of work for us if part of the work is knowing what the digits of pi are out to about 30,000 digits. I think most people here don't know that many digits of pi. So that means actually there must be a way to do this without even knowing what the digits are. Interesting ways to do such problems, by the way, are that if you think the digits don't matter, you can pretend that all of the numbers in the grid are the same in some simple number, like 0. If you did that, you'd say that Alice's number is 0, Bob's number is 0, and so the ratio is undefined. Then that's bad. So don't use 0. You could try to use 1 instead. And if you use 1, if Alice has each of the row sums as 1, 1, 1, 1, 1, 355 of them, then each of Alice's numbers would be 355. And if Bob was doing this for columns, each column has 113 things inside it. So Bob would find 113 as every one of his sums. The average is 113. And you'd get an answer of 355 divided by 113. That's not a proof, though. Here all we did is we said, since somebody is asking me this problem, there must be an easy way to do it. There must be an easy answer. Let's talk a little bit further about why that's actually correct and why it actually is safe to really not worry about what numbers there are inside. The way to see this is to think about the grid. So what is Alice actually doing? What Alice is doing is that she's first going to add up all of these numbers. Then she's going to add up all of these numbers. And she's going to do that for every single row of the grid. Now, she has calculated 113 numbers. If she has 113 numbers, now she has to calculate the average of these 113 numbers. How do you do that? Well, you add all of these numbers together, and after you're done adding all of those together, then you divide by 113. But wait, look what she's done. She's added up all the numbers in each row and then added up all of those rows. Actually, all she's done is she's found the sum of all of the numbers in the entire grid. So what that means is that Alice's average is just the sum of the entire grid. The entire grid. I'll write the sum of all divided by 113. Well, once you see this, then you can see what Bob is doing. Bob is going to do this by column. So what Bob will do is Bob will first add up each of the columns, and then Bob is going to add all of the columns together, which effectively adds up everything in the grid, and then divide by how many columns there are, which is 355. And so what that means is that Bob's average is also the sum of all, but now it's divided by 355. And once you see this, then that means that if I take Alice's average divided by Bob's average, sum of all cancels, and this divided by this is exactly 355 over 113. So the answer is 355 over 113. But what if I wanted to know that as a decimal? Actually, I chose these numbers on purpose. There's a reason why all of these numbers are picked. And in fact, there's even a reason why the numbers that I chose to put everywhere are pi. It's actually because this particular ratio, 355 over 113, has a really nice decimal approximation. If I write down the first few digits of this number, you can take out your calculator, try this. You will find that it's 3.14159, and then it's a 9. By the way, I told you I know some of the digits of pi. The digits of pi that I remember are 3.1415926. This number, 355 over 113, is actually one of the best approximations to pi with a rational number, which is written as a fraction with two integers. It was actually discovered more than 1,500 years ago by a Chinese mathematician, Zhu Chongzhi. And he was actually an astronomer. He was a fantastic astronomer as well. This number, I like to say, is also very nice to remember because it has 2 1s, 2 3s, and 2 5s. So the next time, if you ever are playing with pi, if you don't remember enough digits of pi, just remember use 2 1s, 2 3s, and 2 5s and divide. You'll get something pretty close.